So turning back here, um, this week here's this week's primaries. Last week we're looking at potential flows. Specifically, we're focusing on the building blocks for uniform stream and the source sink shown in A and B in the image. However, I left out part C for this week. So in addition to covering part C, which is the vortex potential flow building block, we're also looking at the doublet. So the doublet is a combination of the uniform flow, source and sink in order to create a cylinder, or flow over a cylinder. And obviously, step one, very same as last week, we got to create our mesh, our grid, to generate the images you saw in the previous slides. So um, I'm now going to switch over to my Google. So here I copied over the same library as last week. And additionally, I copied over the same meshing format. Only difference between last week and this week is that our xn and x start initially was a -4 to 4. Now it's and now it's -2 to 2. And for the y start, it was -2 to 2. Now it's -1 to 1. Can someone repost the link to the code for James who just joined? Okay, but that is us making our mesh. All right. So before we basically do any coding, I want to run over the theory of how these things are formed. So let's first start with the doublet equation. I guess first we look at the Rankine body, as you should see in these two images here, Rankine oval, I guess. We created something similar last week. This is when we put a source and sink down just in a free stream and we had a Rankine oval. So I guess some important things to point out is the distance between the source and the origin and the sinking origin. That's referred to as A, which is essentially, it's kind of like, I think it's like the focal distance or focal length. If you look at an ellipse, that's what the term's referred to. And obviously you have this body. So as I mentioned in previous lectures, in order to basically show the influence of two different building blocks in the same region, we just do superposition. We just add everything. We just add up all the psi values, the streamline values, and that shows the influence of your building blocks with one another. So that's why we add up source and sink for this Rankine oval. We derived this in the previous lecture, but for sources, essentially, the psi values of the source are just dependent on the angle because flow comes out radially from the source. Each psi value is not dependent on your radius away from the source because it's the same for each streamline. What does matter is the angle. So that's why your psi source and psi sinks can be broken down into a strength value and an angle value. So obviously, because your source and sink are located at different locations, the angles are going to be different. So for example, in the image here, if we look at a point, so um, yeah, I have a laser pointer here. So let's say a point here, somewhere in your flow field. You want to find, the psi value influence based on the source and the sink. The angle for the source is in red, obviously, so it's a positive theta value. But for the sink, which is you see the blue arrow, it's going to be obviously a different psi value in order to get to the same location in the flow field. Um, Therefore, that's why I highlighted it in red and in blue. Okay, now long story short, I mentioned before as well, because your source and sinks are creating the strong mass, your mu's s has to be the same value. So I isolated it as you see over over here. Now, based on polar equations, in order to obtain theta, the equation is tan theta equals y over x. I didn't have time to write everything out, so I'm mostly going to be explaining it. But essentially, it's here. Oh, here it is. Yeah, so tan angle is equal to y over x usually. And in these screenshots I took, x2 is referring to y, it's like the y coordinate system, and x1 is referring to the x axis. But yeah, so those are how you convert between your Cartesian coordinates and your polar coordinates. It's using these identities. And there's another identity to convert between the combination of two different angles. And that's what we're going to do. So we basically use that conversion to convert from your top equation here. You use these trig identities to obtain the bottom value here. So for for a doublet, for a doublet, psi is equal to negative source strength times arctan of this combination here. You can do the math yourself, or maybe you can ask me and I can send an email of my work, but you can go from the first step to the last step using these identities. Now, here's the more important part. With this identity, we're gonna now go from a Rankine oval, which obviously is an ellipse, to a cylinder. Now, how do we do that conversion? We basically, well, first up, we're gonna use a small angle approximation. If we sorry. So in order to go from a Rankine oval to a cylinder, you want that your source and sink basically be on top of each other. As we saw from the last week's primer, as we move the source and sink closer to each other, you saw the shape of a cylinder start to emerge. So we want the source and sink to basically essentially overlap each other. However, at least in our code, when they overlap each other, they just cancel each other out, and we don't want that. So we're gonna try to go through the math to basically overlap the source and sink without making those two influences go away. So that's where we let a equal 0, because obviously if your focal distance or the distance between your source and the center and the sink in the center is 0, they're on top of each other. So if we let a equal 0, what's going to happen to the inside part of your arctan? So it's going to be 2 times 0 times some y value divided by x squared minus 0 plus y squared. So essentially, it's going to be arctan of 0, right? And be arctan of 0, 0, because it's going to 0, we can make the small angle approximation then. And because of the small angle approximation, arctan of 0 is going to be 0. So then we can basically we can say the angle inside is small enough where we can take it out of the arctan and just ignore the arctan entirely. That's what we did there. So now we've extracted this term. And after we extract this term, once again, a is still equal to 0 because we want to overlap the source and sink. However, if we do so, we're going to get 0. So in order to avoid psi equaling 0, which in that case everything cancels out, this term at the very start here that we haven't looked at yet, the source strength, the closer you are to the center of your source of sink, the stronger the magnitude is. I explained in the previous lecture. The closer you are to that point, the stronger the higher the psi value is. Therefore, we're gonna also assume that assume that this value here, your source strength, is gonna be infinity. So infinity times 0. So usually you have to go to L'Hopital's or some other rule to determine what's larger or what's not. But this kind of contradiction of 0 times infinity, or essentially some very small value times a very large value, we're going to now just concatenate those two terms, A and US, to become a new term, mu D. And that's going to be our new source strength value. And this source strength is based on a formula that I showed once again in the previous lecture for source strength. Only change we're going to make is now we're going to reterm sigma to kappa here. Now, we implement this term here, and here's our new sets of equation for the doublet. Any equation on the math or the theory behind that? Okay. If not, that is the equation for the doublet. That is how you make the cylinder, essentially. And we've already seen this already in the previous lecture, so I'm gonna skip over the image. But now let's go look at the vortex. This is gonna be a little easier to go through. So vortex are essentially points in which flow rotates around. So flow isn't spawning out of it, so we don't really need a counter vortex to counter it out. But yeah, flow is going around it. The closer you get to the point, once again, the faster flow is. The further you are away from the point, the slower the flow. Similar concept to the source. The only main difference, once again, is obviously flow is in the Bragg direction, where in which case the source think it was. Flow is now in your I think it's tangential direction, essentially just the theta angle. So it's in their tangential direction, and we're gonna term source strength with gamma, and we're gonna divide by 4 pi r. I think it's because you're looking at angular velocity instead of vorticity, and then there's the two comes in. Long story short, it's just some strength divided by some constant. That's the main thing. Now, because u r is equal to 0, this first equation here cancels out. Whereas for the source and sink, it's this term here that cancels out. For vortex, this first term cancels out, the VR term. Now, UR. Now, with u theta, we have a term here. It's negative gamma divided by 4 pi r. Therefore, we do, I think it's like a separation of variables to differentiate our answers. And when we do so, you're going to obtain a psi value of gamma over 4 pi times the natural log of r squared. Um, yeah. So one quick thing to note. Um, the because I put a negative sign here, our convention is going to be the following, which is positive gamma value refers to clockwise rotation, whereas negative gamma values refer to counterclockwise rotation. Just something to keep in mind. Because I put this negative sign, our convention is going to be a little different. But once again, as a result, we can obtain our psi and our UV values, which is what we want. Any questions on the derivation for vortex? It's very similar to source missing, and obviously much more simpler than dealing with the doublet. Okay, if not, let's get our code from the link I sent you guys, and I'm gonna show you what happened. Yeah. So this first function here, this is how you get the velocity for doublets. So you input just your strength, which in our case was kappa, and then you put in here the x and y location for them for the doublet, and then you put in your flow field, your grid, which is your uppercase x and uppercase y. So I'm gonna grab that, and on top of that, I'm gonna grab my second function, which is get streamline, which gets stream function for doublet. Same parameters, but instead of getting a u and v value for velocities, you get psi value, which is what we're gonna use to overlap our building blocks. So first I have a mesh. Now I have the functions in order to generate the doublet stuff. Okay. So like I said earlier, we need a strength for the doublet, and we need a location for doublet. So I'm gonna copy those over. And on top of that, it's we don't want just the flow of a cylinder. We want flow of cylinder in a free stream. So we also have our free stream components here. We have the u velocity, v velocity for the free stream. We have our stream function, which is the psi values. So let's copy those over. So this here, or this quote here, we obtain all of our free stream value like requirements, UV values and psi, but we still need to do it for the doublet. So for the doublet, we use the new functions that we obtain here. And these will give us our UV values and our psi values for the doublet. Okay. Now, obviously, before we plot anything, we got to do superposition. So essentially we add up all the different terms. And now we can plot it using the plotter tool. So I'm gonna jump to new line of text. So all the math is done up here. I'll run it first. That's all the math. Now I'm gonna copy my plotting tool, which I have sent in the previous primer. It was on Canvas in some file, but now we can plot this. So plotting, x, y for the grid, and then u velocity for the cylinder, v velocity for the cylinder, and then streamline function for cylinder, we get flow around a cylinder. One thing I want to do real quick is actually remove the free stream part. I guess I just do this. So I want to plot just the doublets, just the values of the doublets, just to show you what the doublet looks like without the flow. So doing so, you get just essentially it's called a dipole source. It looks like a figure 8. That's what this function is making. But when you attach a free stream to the overall field, you have flow over a cylinder. Okay, so if your code doesn't work, let me know, but this is what you should be expecting to get. Now we're gonna do one more part to our code. Let me go through the slides first. I think I need to show the slides before I talk about that. Oh, so okay, actually, second up, I need to plot my vortex. I want to show the vortex. So in the next coding block, I have my get velocity for vortex and get streamline function for vortex. Same concept. Instead of all the differences, instead of now having the equations for the doublet, equation for the vortex. So paste it over. So similar story. We have a strength of the vortex, but instead of being kappa, now it's gamma, and then we have location of vortex. And from that, we can compute the u and v velocities for the vortex and the stream function for the vortex. And then we can plot it, which is what I'm going to do. So as I mentioned, because we have a positive gamma value, we're going to have clockwise rotation. Um, I guess the convention maybe will be clear afterward, but for now, positive means clockwise, negative means counterclockwise. And you look at this image shown here. And that's what you'll see in my slides too. We'll get this image. Try checking different psi values. If you change the psi values in the plotting parameters, you'll see that the smaller the value is, the closer you are to your vortex. The larger the value is, the further away. Actually, I think I got the reverse. Let me try that. Let me actually test that. So currently it's at 0. Let's say I increase my levels to 10. Psi value is gone. Maybe a 1. Okay, so the smaller the value is, or sorry, the larger the value is, yeah, the further away you are. And then I guess the more negative you are, the closer you get. Try that. The more, so yeah, so as you increase the values in the positive direction, the further away you move from the vortex, the more negative you get, the more close to the center you get. So that's what I meant. And it's all based on, once again, the psi function shown down here, because it's based on the log function or natural log function. Okay. So we did this already. I showed that in the code. Now, what I want to do is, in regards to the cylinder, because we've created the cylinder using the doublet function and put the doublet in some kind of streamline function. So all the parameters we've basically inputted so far is obviously kappa for the strength, and then location for the doublet, and then free stream velocity. So none of this really tells us what the radius of our cylinder is. Like we put in these parameters and we get a cylinder. We don't know the radius of the cylinder, which is a very important detail. So in order to obtain that radius, we're gonna look for this thing called stagnation point. So what the stagnation point is obviously you have a cylinder sitting here, and your free stream comes in and hits your cylinder. When the free stream velocity from the flow field hits your cylinder, what happens is obviously at the head of the cylinder or the front of the cylinder, it's gonna stop because you can't penetrate through the cylinder. It's a solid object. So what the flow does is it's gonna split up and divert around the cylinder. So at that point, that stagnation point, your u velocity equals 0, and then it spawns in the v velocities. So we're gonna look for points in which u equals 0 at the front of the cylinder. So I wrote these notes on myself. So here's the equation for the u values of free stream. As you see, free stream is obviously just u infinity, and plus doublet, which is negative kappa over 2 pi, and then these terms here. You can find these equations in my previous last week's lecture. But now what I'm going to do is convert from Cartesian coordinates to polar coordinates because it's easier to work with. And I do that conversion here. It's just some polar coordinates equations that you can find online. But essentially, I have some r squared terms that pop out. I'm going to cancel them. And as a result, I have the following: u infinity minus kappa over 2 pi times cosine 2 theta, because cosine squared theta minus sine squared theta is cosine double angle formula, divided by r squared. Now, once again, I'm looking for the stagnation point where u equals 0 at the front of the cylinder. Front of cylinder implies that the r, or radius, is equal to lowercase r, which is what we're trying to solve for, essentially. Lowercase r is going to be the cylinder radius, and then front of cylinder is theta equals 0. So plugging these terms here, u at r, lowercase r equals lowercase r, and theta equals 0. U infinity minus kappa over 2 pi times cosine of 0, which is 1, divided by r squared, which is the radius of the cylinder, equals 0. Now we're going to reverse this and solve for r. Now, r equals square root of kappa divided by 2 pi free stream velocity. So as you see, based on our inputs, which is obviously the strength of the doublet and then the strength of your free stream in your flow field, these two parameters are actually important because obviously they're what's being used to calculate r, which is the radius of your cylinder. So this is the equation for radius of cylinder right there. Okay, any questions on derivation or logic to get to this point? Okay, if not, we're gonna use this value for something for um visual purposes, I guess. So now we're gonna just plot your stagnation points in green, and we're gonna color the cylinder in red. So in the code, there's a way to do that. It is scrolling back up. This point here. Here, calculate cylinder radius to add to the image, and then calculate stagnation points, which is same math, to put green dots to show where the stagnation points are. So I slap it right here. Underneath the plotting. So after the plotting line, I paste that code in. I run it. And as you see, it colors in the cylinder and adds the green stagnation points. Okay. Now, time for the last part of this lecture. And well, yeah, we're actually gonna finish early, which is great. Oh, um, so what we're gonna do first, before I go to the next slide, actually, we've seen this already. This was from last week. We want to see something new. So how are we gonna see something new? We're now gonna add we're now gonna add the vortex onto this. So to add the vortex, obviously you just use it's superposition. So now you just add the u, v, and psi values of the vortex onto what we already have to see what the influence of the vortex is. Um, okay, so yeah, for now, I'll copy this, put it down here. In my fourth line, or fourth coding block, I don't know, I'm just call it u total because I think that's why I call it in my code. I just gotta check my code. Okay, here it is. Yeah, I'll just copy this. So now it's not just doublet on the free stream flow. It's doublet and the vortex on the free stream flow. So I mean, I just added this extra part on. That's all I did. And then obviously now I need to plot it. Sorry. Okay, I'm gonna skip that part. I'm just gonna plot it. So when I just plot it, like without really knowing anything, here's what I'm gonna get. So obviously you're gonna see that you see that cylinder shape like still present in the center of the screen. But now your free stream isn't going directly from left to right as it usually is. There's a bit of curvature to the flow field around your cylinder. It appears to be the flow is kind of has an angle of attack going upwards, and then it kind of dips down afterwards. As a result, you see like our contour line, goes up and down. So I guess the first thing I want to do is I want to recapture the shape of my cylinder, not with like plotting the red like plotting the green circles and the big red circle. I want to get this image of my cylinder via the contour line, which is this red line here. So how to do that? So in previous, so previously, um, remember once again, the contour line is based on your psi values. So previously there was no gamma section. So imagine it's just this part here. Show with my highlighter or laser pointer. It's just this part here. So when sorry, so this next line here is I convert like this just this side here into polar coordinates. So I convert this to polar coordinates, and I go down to here. So the first two terms of the psi function is shown here. U infinity r sine theta times 1 minus lowercase r squared over lowercase r squared. So at the edge of my cylinder, which is just r, for doublet in free stream. So imagine no vortex in this math. So if I pick lowercase r, which is where I'm located radically, to be uppercase r, which is my cylinder, 1 minus uppercase r squared over lowercase r squared, or over uppercase r squared, because lowercase r is uppercase r, 1 minus 1 equals 0. Therefore, when psi is equal to 0, your contour line will show the cylinder itself. However, this is not the case anymore because now we have our vortex term. Our vortex term makes it so that when we input psi of 0, we do not get the cylinder. That is not where our cylinder is, as you saw on the code. So to get the red line to be on the cylinder, we have to now consider this term here. We know this the first two term equals 0, so it goes away. So what value must psi be in order to get the red line on the cylinder? So is it here? Gamma over 4 pi times log of lowercase r squared. We want lowercase r, or we want lowercase r to be equal to uppercase r, because then we will be on the cylinder surface. So therefore, psi, instead of psi equals 0, we want psi to be equal to gamma over 4 pi times log of r squared. So let's put that into the code, or let's put that into our code. So here it is. As you see, gamma divided by 4 pi times log of r squared. R was calculated earlier because it's the same cylinder. Cylinder hasn't really changed. It's just the flow field that's really changing. So boom, there you go. Our contour line is now showing the cylinder surface. And that being said, let's also put in our other code, which is just sorry, I'm missing some code up here. So same principle as we did for just the cylinder itself. You go through the same math, which I didn't really show, but you can also obtain the new stagnation points, which is where the flow interacts with your surface of cylinder and then diverts. Okay. So yeah, as you see, adding the vortex to your superpositioning the vortex onto your flow over cylinder, your stagnation points move downwards, first of all, and the flow field is not symmetrical along the x-axis anymore. It's still symmetrical on the y-axis though. So yeah, so this is flow over cylinder with vorticity. So I mean, so obviously, if you just think about the math, all we did is we add vortex to this I guess all these other building blocks, right? But another way to think about what we're seeing right now is this is what happens when you have a cylinder in free stream flow, and then your cylinder starts rotating. Because we can imagine, in a way, the vortex is the cylinder spinning. So our cylinder spins, and this is what happens. Here's one way to describe what's going on. So once again, we picked the positive gamma value, right, for the vortex. Positive gamma value means clockwise rotation. So therefore, the cylinder is, in a way, also rotating in a clockwise fashion. So when the cylinder rotates in a clockwise fashion, what happens? Maybe I show my slides. Okay. So once again, cylinder is rotating in a clockwise fashion based on the vortex, or due to because of the vortex. So it's rotating in a clockwise fashion. So remember, without the vortex, the free stream velocity would just be going like this, from left to right. So now, with the inclusion of the vortex, what's going on? So the clockwise rotating fashion for cylinder implies that it's giving the cylinder velocity at the top of the cylinder. It's giving the cylinder there's degree of velocity going to the right, whereas on the bottom cylinder, there's be speed going to the left. So obviously, there's now this juxtaposition, right? Top side cylinder has velocity that is in line free stream velocity. It's going with the free stream velocity, whereas on the bottom of the cylinder is going against the free stream velocity. Therefore, the overall velocity on the top of the cylinder is much higher, whereas the overall velocity at the bottom of the cylinder is much lower. Therefore, that causes the stagnation points to shift to the lower side. So I mean, yeah, so cylinder is rotating, so we get different flow field. So what? So I'll show you now why it's important. So same things we did from last week. We're now going to try to obtain the pressure distribution along the cylinder. So to do so first, the whole concept obviously is here. We want to calculate pressure coefficient. So to do so, we start with Bernoulli's equation, and then we rederive it to be that the pressure coefficient is equal to 1 minus the velocity at some location divided by the velocity of the free stream velocity squared. So we want to obtain um, the velocity of your flow field. So to do so, we're going to basically use the SciPy interpolate tool that is given in the library to essentially um, set up functions in which we can basically input a set of a range of coordinates in which we're interested in, obviously, which is the cylinder, the coordinates of the cylinder. We input in those coordinates and it's going to spit us back out the array of the associated u and v velocities of the flow field. And make sure to let me know if it doesn't make any sense. So let's do that first. Okay. So first up, first code I'm gonna put, so this is my fifth and last code block. So once again, using regular grid interpolator, which is a function, I'm basing, hey, for the function that I'm interested in making, which is the function is called uinterp, for this function uinterp that I'm going to create, the parameters are going to be y and x, because y and x of this 2D array of all the u values in the flow field. So I'm gonna give you a y value and an x value for this, and you're gonna spit back out what this what the what is this the u value of that location. Same for v. We set up the same function for v velocity. So that's what I did there. Now, what I'm gonna do is I'm not gonna give it the shape of the contour lines in order for it to find the associating u and y values on the surface of the cylinder. That's what I'm interested in. That being said, though, we don't need to use the red line. That's what I did in the previous lecture, but honestly, it's pretty complicated. There's an easy way to do this. Let me show you what I did. So here, all I did is I said, hey, theta is 0 to pi. So essentially, for cylinder, 0 all the way to pi. So just from the front to the rear. So from 0 to pi, I want to get the associated x coordinates and the associated y coordinates based on these equations, which is just equations for a circle. That's all I did. R times cosine theta for x and r times sine theta for y. And doing so gets me the following image here. So that is the upper half of the cylinder, right? And once again, r is the cylinder radius that we solved for earlier, so it's right. Okay, so that's the only purpose of that part. Now that I have the shape of my cylinder's upper surface, I'm now gonna put it into sorry, I'm not gonna put it into here. So this is the x and y values for the upper surface, and I'm gonna basically use it as a coordinate input system for the u function that I made and the v function that I made, and basically zip it, which is just concatenate it into an array, and we'll call it velocities. And then with my u and v velocities, I essentially take the square root of them squared, which gives me the magnitude of the velocity overall. That's what these two lines mean. So just to show one more time, like last week, what I'm doing. So with the first line of what I just inputted, I'm zipping all the associated u velocities in the first column, and all the associated v velocities in the second column, based on the list of coordinates that I input in, x upper and y upper. So now I have the corresponding u and v velocities. Then in the second line here, I I basically take the first column, square it, and sum it with the second column squared, square root them both, and then I get obviously my magnitude of the velocity. So not just u and v, it's the overall velocity magnitude. And now it's just one array, or that's why it's one array. So using the formula I showed you earlier in my PowerPoints, I can now obtain this associated coefficient of pressure, Cp upper. That is the pressure. That is what we have solved for is the pressure distribution on the upper side of the cylinder. But that alone isn't really meaningful to us yet. So now what we're going to do is find the pressure distribution on the lower surface of your cylinder, as shown here. So all I did, basically exact same as the top, only difference is now I put y equals negative, because obviously now, instead of looking at the top side of the cylinder, negative makes it look at the bottom side of the cylinder. but the exact same code though, otherwise. So now I have pressure on the upper surface and pressure on the lower surface. I'm not gonna plot these two together, and let's see what happens. So in blue, that's the first thing we did. Blue is upper surface of cylinder. As you see, it starts obviously at the front and rear of the cylinder has the same pressure because obviously it's the exact same point. But for the upper side, we see pressure dropping. Remember, upper side has the faster velocity. Just keep that in mind. So pressure is dropping until it gets to the very top of the cylinder. Then pressure then slowly increases until it meets back up to the rear. And once again, upper side has faster velocity. Meanwhile, in orange, which is the lower surface of cylinder, with the lower velocity, pressure increases and kind of holds there, and then decreases. So pressure on the upper side of the cylinder is in the negatives, which means the pressure is lower on the top of the cylinder, whereas on the bottom of the cylinder, pressure is much higher. Now, and just to reiterate, when I say pressure in this case, I'm referring to static pressure, not dynamic pressure. That's different. Because once again, upper side of the cylinder is faster, therefore it has higher dynamic pressure. Higher dynamic pressure means lower, um, so sorry. Um, velocity on the upper side of the cylinder is faster, therefore you have higher dynamic velocity. But based on this curve, this plot here, CP being negative, you have a lower stagnant pressure. So higher dynamic pressure, lower stagnant pressure. Whereas for the bottom of the cylinder, you have slower velocity, which means you have a lower dynamic pressure. But as you see, the CP plot here is higher, so you have a higher static pressure. So low dynamic, high pressure, high static pressure for bottom surface, high dynamic pressure, low static pressure for top side of surface. And the whole point is, I'm trying to say is your dynamic and static pressure terms, when they add up, they should be equal everywhere in your flow field, at least for a potential flow case. So it's kind of like a trade-off between those two terms. Now, why is it important? The reason it's important is the static pressure part, which is what you're seeing on this plot here. Static pressure for the upper side of the cylinder is lower, whereas static pressure on the lower side of the cylinder is higher. Therefore, there's higher stagnant pressure on the bottom cylinder, lower stagnant pressure on top cylinder. This pressure difference creates a force. So now there's an upwards force on your cylinder. And essentially what's going on is because your cylinder is rotating in a clockwise fashion, there is a positive lift force being experienced by your cylinder. Your cylinder is experiencing an upwards force. And that is one of the most basic principles for lift. This is called the Magnus effect. You can look more into it. But by rotating the cylinder in a clockwise manner with a flow field going from left to right, your cylinder is experiencing lift. Okay. That's it for my slides today. I will post the results. And yeah, once again, got all this from AeroPython. And I'll take any questions now.